And the recording is for YouTube. So if you want to hop off right now, or if you have something, I know some people have other clubs and engagements, you can always look at the lessons on YouTube. So we're going to start off with time and space complexity. So first of all, defining time complexity. Time complexity is basically a function to describe how long an algorithm will take to execute on any given piece of data based on input size. So we're talking about an input variable, and in this document and in most documents that you're going to find, the input variable is size n. And then time complexity is defined using big O notation, which is literally a big O, just like a function, just like f of x, except for it's O of n. So what you may be asking, what actually does this mean? What is the O of n? What is O of n squared? So O of n squared, or O of n, is generally referring to the upper and lower bounds of the number of operations that are taken by an algorithm. And since it can describe either the upper or lower bounds, generally people actually just use it for average. Which means that if something has an average runtime of O of n, but it can take much longer or much shorter than that, we're still going to say that the time complexity is O of n. So I'll get to what specific time complexities are later. Big O notation also ignores the coefficient, since we only really care about the exponent or the leading term. So something like 2n would reduce down to O of n. O of n squared plus 3n plus whatever else you want will always reduce down to O of n squared.
This is also important when you have multiple for loops. For example, if multiple algorithms are in phase, you're going to only take the slowest one. So that means if you have like a for loop, if you have in a program, you have one for loop, and then you have inside that same program, you have another section that takes two for loops within. You're gonna count the slowest part of the function.
Okay, so you may be asking, who really cares about this stuff? And really, the most useful use for O of n and big O notation is to measure and to check if an algorithm is going to be way too slow or just right for any given problem. So if you have a problem in a competition rather, and the problem has a sample input, and it says the input can be between 0 members long and 10 to the 5, you can reasonably assume that the algorithm is not going to run in n squared operations, because 10 to the 5 squared is 10 to the 10, and 10 to the 10 operations is a lot. You can assume that the algorithm that you're trying to make to solve this problem is going to be running in either linear or logarithmic or something much less than polynomial time. So a real world example of this would be if you had something that took 1,000,000 seconds, I think that'd be around a week of time. But then if you accidentally got 3 more zeros, so 10 to the 6, 10 to the 6 becomes 10 to the 9. 1,000,000,000 seconds is more than 18 years. So what we're gonna go over now is some examples of specific time complexities. As always, if you have questions, you can unmute and ask, or you can ask in the chat. So constant time is notated as O of 1, which means that no matter the size of the input of the algorithm, it always takes the same amount of time, same amount of operations, which is 1 or a constant number of operations. So in this example here, we have an array, which is x, and in the array, we have a set of values, and constant time operation would be something like accessing the third index of x, which will always map to 7. Now, this only takes one operation, no matter the size of x. So if I were to continue adding to x, I could reasonably assume that it would not change the speed of accessing anything in X. Something that is linear is a linear search, which is like basically iterating through an array to find a value. If you want to find the 5 in X from this X, basically what we're doing is we're going to check the first element, then we're going to move on to the second element, to the third element. And on average, if you think about it, the element could be anywhere in X, which means the average case is that it's in the middle of X. So that would mean that the average runtime for this linear search is half n. But if you remember, we kind of disregarded the coefficient, so we say that it runs in linear time. And then the last example on here that I've actually written code for to visualize is O of log n. Now, log n, if people don't know what log is, it's basically a function for finding the, it's a function for finding the number of times some base value will go into another number. And generally, when we're talking in computer science, the log will have a base of 2 because we work with binary very often. And an example of something that runs in log n time is binary search. Now, don't worry if you don't understand or know what binary search is, because we're going to be going over that briefly in, I think, another lesson next week or in 2 weeks.
Yeah, next lesson. So in 2 weeks, probably.
Okay. And the gist of it is that it recursively halves the array. Sorry, let me let this guy in. Okay. It recursively halves the array and then searches each half for the value you're searching for. And if it doesn't find, or rather, it compares the value you're looking for in the two halves. And you can recursively go down and basically you're only halving the array. So if you think about it, that's going to be in base 2 since half is 1 over 2. So this specifically would be log base 2 of n, this average runtime, but we don't really care if it's log base anything. We just care about the log part. Now, I hear there's a table that I've made for the various time complexities that we're going to be working with, and the time complexities that we're going to be seeing in most of the algorithms that we're going over. Some of them might not be within this set of time complexities, but I think the majority of algorithms you're gonna encounter in pretty much all of computer science is gonna be running in one of these notation times. So we already went over constant, linear, and logarithmic, which is with their respective examples. O of n log n is called, and I didn't know this, but it's called linearithmic. People generally just say n log n. And it's a good indicator that the algorithm you're working with is a sort algorithm. So something that takes an unsorted array of values and puts it into order. Things like merge sort and quicksort are in n log n time, although slightly different, and we'll get to that when we go over merge sort and quicksort. And then we go on to polynomial. So n squared, n cubed, n to the fourth, and beyond. Those all fall under polynomial time. So a good way to visualize this is if you're iterating an array in a for loop, and then you nest another iteration in that for loop, that would be n squared. And the third for loop inside those would be n cubed, and so on and so forth. Exponential time is for finding all these subsets in a list. So that, or rather, an example would be finding all subsets in the list. That would be working with k. And so wait, let me get back to k. So polynomial time and exponential time both have this variable called k. K is a constant generally that depends on depends on something else within the actual problem. So sometimes you might have n squared and cubed. K would be 2 and 3 respectively. Something in exponential time could be 2 to the n, 3 to the n. So k would be 2 and 3 respectively for that. K is just basically specifying, in this case, how bad, or no, how long it's going to take. And then finally, factorial time. One example would be finding all permutations in a string. And for anyone, I hope everyone knows what factorial is, but for anyone who doesn't know, if you have 5 factorial, it's 5 times 4 times 3 times 2 times 1, so on. And so these last three, as you can imagine, they explode really fast. And what I mean by they explode is that they take a really, 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 really long time once n goes towards larger numbers. As you can imagine, 100, 2 to the 100 is a very, very big number, but just log 100 is actually quite a small number. So we're going to tend to see algorithms that fall under the first 4, or rather the first 3, since constant time isn't really something that algorithms deal with. But we will see for algorithms that are examples of these 3 notations here. Polynomial time is something that you're going to see a lot, I guess, in n squared and n cubed, but not much more than that. So n squared, you're going to see a couple of things for specific problems. N cubed, there's a really simple to write pathfinding algorithm that we're going to go over later. But more than n cubed, I doubt you're going to see much of that. Finally, space complexity. If you understand time complexity, space complexity is nearly identical. Space complexity is basically just how much memory an algorithm takes over the course of its execution. So instead of counting how many operations an algorithm takes on its input size, we're actually saying how much memory in the computer does the algorithm take depending on its input size. This is important because you don't want to have an algorithm that takes n squared memory and that could have input sizes that are very big, because your computer is going to run out of memory, the algorithm is going to crash. So it's good to know what space complexity is too. A good example of this is the Fibonacci sequence, since if everyone should know this as well. I'm not assuming anything though, but you only need the last 2 numbers to calculate the next number for Fibonacci. So even though it would take, to get the nth Fibonacci number, it would take n operations, or the order of n operations. It only takes the last 2 numbers into account, which can be thought of as a constant amount of memory. So that is it for the actual lesson part of this meeting. If anyone has any questions, can speak up right now. And I guess the main thing is that we want suggestions on how you guys liked it, and I will stop the recording.
I mean, it's always important to, like,